Okay, welcome to Note Set 18. We're moving into Chapter 4 here, and we're going to talk about a concept called orthogonality. So we've already talked about orthogonality of two vectors, but we're going to see that this concept allows us to think about much bigger ideas than just whether two vectors are orthogonal to each other. So, just reviewing what we've seen long ago about orthogonal vectors in the context of their dot product or inner product, as I prefer to say. So if their inner product is 0, we say the two vectors are orthogonal. So here's just two ways to write it. There's one more way to write it with the angled brackets with V and W in there. So that's the way that I prefer to write it, but the book tends not to use that, so I've avoided it here, except, well, I can't always avoid it. So if we look at two vectors that are orthogonal, one property that we get from that is that the norm of the sum of them is equal to the sum of their norms. So that comes from the two vectors being orthogonal, and we can see this if we notice that the right hand side is can be written this way, and we just expand that out. So that's the length of vector v plus w, and if you just expand this out, so you'll get v transpose times v. You'll get W transpose times W. That's these two terms. And then the cross terms will all go to 0. There will be two cross terms. Those will go to 0 because of that. And you will be able to establish this result. So that's a nice extra little side result there for orthogonal vectors. So we can extend this idea of orthogonality, not so much the sums of norms of sums and things, that was just a little side thing, to subspaces, spaces, and matrices. So it comes from when we think about A times X. So on the first level, we're just thinking about it as numbers, things that we're doing with numbers. The second level we think about when we do AX is that we're combining column vectors. And then the third level, and we've been starting to talk about the subspaces that arise from thinking about this AX operation. So we've got the column space, we've got the row space, we've got the null space and the left null space. So we've been talking about those subspaces. And we would now like to think about those subspaces in the context of orthogonality. So if we have two subspaces, let's just call one V and we'll call one W. So there are two subspaces of some vector space. We say that those two subspaces are orthogonal to each other if every vector V in the first space is perpendicular to every vector W in the second space. So another way to write that, the way that a mathematician would write it down in shorthand, we say that V and W subspaces are orthogonal if VTW is equal to 0 for all V in V and all W in W. So here's an example. Are these two subspaces orthogonal to each other? So we've got the W subspace, which is this plane. We've got the V subspace, which is the other one. And you might think, we should show the origin. Let's say the origin is there. We might think that they are, because we would say, well, here's a vector, there's a vector. They're orthogonal. These are all orthogonal. Any vector I draw here seems to be orthogonal to that one, but wait a minute. Look at that vector is in both. as is that vector, is in both. And those vectors are certainly not orthogonal to each other. In fact, they're collinear. So any vector that lies where the two planes intersect will be not orthogonal to each other. And yet they, even though they're in both, we could say one's in V, one's in W, and the definition does not hold. So those are not orthogonal subspaces. But here's another example. So suppose we've got V is the room of the floor. So, again, you have to remember these things go on forever. And we're not interested in the green and orange walls. What we're interested in is the line where they intersect. And remember, that will continue on down underneath V. So let me clear this out. What we really should think about is this line that comes down like this to here, goes through the floor of V, and then comes out underneath down below. So that's W is the line, V is this plane, and those are orthogonal subspaces. So there is no pair where one is in W and one is in V where the two vectors are not orthogonal to each other. And so what we see here is that, we can, in a more theoretical course, we would prove this, that the orthogonality of two spaces is impossible if you add up the dimension of one space plus the dimension of the other space, and that is greater than the dimension of the whole space. So that's the case that we had on the previous slide. We had V has dimension 2, W has dimension 2, so those add to 4, which is greater than the dimension of the whole space, which was 3. So that's a nice rule to keep in mind. Now let's try to tie these things together to our 4 important subspaces. So one observation is that when a vector is in 2 orthogonal subspaces, it must be 0. That's the only thing that we can have in common. So if we go back to our example here, there's one vector, the 0 vector, that lies in both V and W. So that's the only one. That's the only vector that can be orthogonal to itself. And so if we look at our 2 spaces here, there's one vector there at the corner. That's why we set these things up. And what we'll see as we go through this is that all the other vectors are orthogonal. So that in fact, the row space of matrix A and the null space of matrix A are orthogonal to each other. And the only vector that is in common to them is the 0 vector. So we're stating that here, N of A and C of AT are orthogonal subspaces of Rn. And the short answer is because AX is equal to 0. Well, we'll explore that a little bit farther, but let's just look at an example here where we're looking at the rows of A. So those are the things that make up or span the row space. And so here is a vector that is clearly in the null space. And you can see that the reason that it's in the null space is because, well, when we multiply it, we get zeros over here. But what is that multiplication? Think back to the many ways we said to think about doing matrix times vector. Well, it's this row inner product with the x, and it's this row inner product with the x. So we're doing inner products, and so we're getting inner products that are equal to zeros. So that means each of the rows is orthogonal to that one vector, and that vector is what is a basis for the null space. You can show that this matrix has a null space that has dimension of 1. So we see an illustration here that this idea seems to be true. Let's see a little more clearly and more generally why this row space is perpendicular to the null space. So if we think about this, well, we just argued that every row of A is perpendicular to every solution of AX equal to 0. So if this is any vector in the null space, we know that AX is equal to 0. And so what that means is it must be orthogonal to every one of those rows. And those rows span the row space. Now we say, technically all we've really done is shown that it's orthogonal to each of the rows. And then we can make a word argument that says, well, those rows span the row space, therefore the null space, anything in the null space must be orthogonal to anything in the row space. But it's a little bit easy. It's pretty easy to check to actually show that this is true for all possible linear combinations of the rows. So let's do that. Let's say that let X be in the null space. So in other words, X is any point in this null space. And when we say any, it means that we're not just saying this is going to hold for one special one. What we're really saying is this will hold for every possible vector in the null space. So let X be any vector in the null space. Now we let V be the rows be in the row space. So V is any vector here in the row space. And let's see if we can show that any of the anything in the null space is orthogonal to anything in the row space. So what we need to answer is, does the inner product between V and X equal 0? Well, since V is in the row space, that means that it can be built from the rows of A, and so that means that there is some vector y that when we multiply A transpose y, we get the special selected V. Not special, but just the any V that we picked. So then let's look. V inner product with X is equal to, let's put in what we had for V. So there is some y that allows us to write V that way. Let's write out this inner product in terms of matrix vector multiplication. So we're going to take the transpose of the thing in the left position. And then properties of transpose, we interchange the order and transpose everything. So we get y transpose times A times X. But here's the key. That turns into 0 because X is in the null space. So this is the key. We get this here because anything that is in the null space, or I'm sorry, anything in the row space ends up giving us something that looks like that. And we end up with the A because of the transpose that occurs in doing the inner product, and boom, automatically we get A smacking against X, which gives us the 0. So that holds in general. So that's a nice little but solid proof. What about the column space and the null space of A transpose, the left null space? Same thing. They are orthogonal to each other. Why? Same exact reasons. We could go through the same argument just switching the roles of A and A transpose. And we would have it. So when B is outside the column space, we'll see that it will lie in this space. And this nulls, well, it won't lie completely in here, but this will suddenly start playing an important role. We won't see that right away, but we'll see that later when we talk about a topic called least squares. And so the error between B and what we can try to, the X that we can pick to try to map to B, we won't be able to map it exactly. This error will lie in this left null space, as we'll see. So not important right now, but just alluding to the future. So let's look at these other two subspaces for this same example. So here we're just showing that same A operating on the vector x that gives us 0. So this is the basis vector of the one-dimensional null space. So the column space, though, is all of R2, because we can see that 1, 5, 3, 2, those are definitely linearly independent. We only need 2 linearly independent rows, or I'm sorry, vectors to span all of R2. So we know that those columns, even though the third one is linearly dependent on the first 2, we've got 2 linearly independent ones. So we are spanning all of R2 with the column space. And so what would be the null space? Well, we can think of a couple ways of thinking about this. So the null space of A transpose, we can try to puzzle that out by looking at A transpose, but we can also remember our dimension rules. So we've learned a couple different things. We've learned that the column space here must have dimension equal to the rank. So since we're saying it's all of R2, we know that the rank of this A is 2. We know that the null space has dimension of, in this case, 2 minus 2. The null space has dimension 0, and the only space that has dimension 0 is the space of just the 0 vector. So the null space of A transpose, for this case, I'm trying to do a curly bracket there, is just the 0 vector. And we also can say this another way. We can puzzle this out another way. We know that the column space must be orthogonal to the left null space. We know that's always true. We've established that already. And since this is all of R2, there's only one vector in R2 that's orthogonal to everything in R2, and that's the 0 vector. So we can puzzle that out yet another way. And so we can also look at A transpose Y is equal to 0 and think about how to solve that. So that just means that whatever vector here has to be orthogonal to all of the columns. So it has to be orthogonal to all of those columns of A. And again, since those columns are a basis, actually span R2, we know that the only way to do that is if Y is equal to the 0 vector. So every vector Y in the null space of A transpose in general is perpendicular to every column of A, and therefore the column space and the left null space are orthogonal, and we could use that to puzzle that out for this example. So we've been looking at these subspaces, talking about one subspace that's orthogonal to another, and we've been talking about the column space and the null space kind of working together, say within Rm or Rn. Now let's try to think about several subspaces that, and we say here, do not carve up the entire space. So in other words, kind of, can we think about some subspaces that kind of don't hit every possibility within the space? And we'd like to know if that's even possible for our beloved row space and null space, or equivalently column space and left null space. So let's just ask some questions here. So we're in R3. We've got 2 lines here, both going through the origin. So they are 2 one-dimensional vector subspaces of R3. Clearly they are orthogonal to each other, and they don't quite carve up, so to speak, the entire space, in the sense that we could find a vector in R3 that we could not write as a linear combination with one vector from one line and one vector from another line, right? So The only vectors that can be written as a linear combination of one from one and one from the other would be those things that lie on the plane in which those two lines lie. So we don't quite get the entire space. And the reason, the real underlying issue here is that the dimensions aren't quite right here. One thing that we've seen about the row space and the null space is that the dimensions of these two add to the full space dimension, right? And we're not seeing that here with these two lines. So let's look at this case here. So here's a simple 1 by 3 matrix A. And if you look at this, we've got n equal to 3. This is an m by n, so m is 1. And we can see that the rank of this is equal to 1. We can see that two different ways. There's only one row, so the row column, the row rank is 1. As far as columns go, every one is just a multiple of the other column. So again, we have rank of 1. And so we know that the dimension of our null space is going to be equal to 2 in this case. So what we would need, we couldn't handle that with two lines, but we could handle that with a plane and a line that are orthogonal. So here's one plane, which could be our null space, since that has dimension of 2, and then the line could be the row space. And I tried to make this line at least somewhat represent that as a column, 1, 2, 5. I don't know how good a job I did that, but that was kind of my intent. So we're starting to see here that there's certain constraints that arise on these spaces. We're starting to see that they're orthogonal to each other, but there's something even more than that. And that leads us to this idea of orthogonal complements. And this is a bigger idea than what we're showing here. We're introducing it to describe our four beloved subspaces, but the idea of an orthogonal complement is a general idea, and we'll try to convey that first and then apply it directly to this scenario. But let's just back up before we go into the complete idea of orthogonal complements and remember what we know already about our four beloved subspaces. Well, one thing we know about are the dimensions. So we know that the row space and the column space have the same dimension, and that dimension is the rank of the matrix. We know that. And we know that if the matrix is so-called full rank, we know that then the dimension of this space will be equal to this, and the dimension of this space will be equal to this. In which case, the null spaces will be left with nothing, because we know that the sum of the two dimensions over here must add up to m. So if the rank is less than n, we're going to have some dimension here and some dimension down here. So maybe our m was 5, and we might have dimension 3 up here and dimension 2 down here. Or we could have 5 up here and 0 down here. So the whole dimension of the space is kind of split between these two spaces. And notice that those dimensions in some sense kind of fill up the full space, because they add up to the dimension of the full space. So we know that. We also know all about the bases of these. So if I give you an A matrix, you can find the bases for all four of these things. You know how to do that. We know that they are orthogonal to each other. So we know that the only element in common between the two over here is the 0, and the only thing in common between the two over on the left is the 0 vector. And we know, and we've drawn a little orthogonality symbol there to show that anything in the column space is orthogonal to anything in the left null space, and likewise anything in the row space is orthogonal to the null space. And so we know that. And again, remember, these pictures are just evoking the idea. They're not precise characterizations. The column space is not some sort of rectangle. Okay, but there's more. It's much more important than that, and that's where this idea of orthogonal complement ties in. The subspaces are orthogonal complements of each other. So we'll see that these two are what we'll call orthogonal complements of each other, and these two are orthogonal complements of each other. So what does that mean? Well, here's the definition. So we start off with some whole space. We've got a whole space. We've got some subspace V, and we're looking for some space that lies outside of V, but still inside the whole space that's orthogonal to everything in V. So the orthogonal complement of a subspace V with respect to the whole space contains every vector that is perpendicular to V. So that means since they're perpendicular to V, the only thing in V that satisfies that is the zero vector. So everything else has got to be outside of it. Okay? And we use this symbol. Let me clear this ink off here for a minute. So we use this symbol to represent this orthogonal complement, and mathematicians will often just refer to that as V perp, or they'll just say the orthogonal complement of V if they want to be a little more wordy. So let's look at an example. This is separate from our four beloved subspaces, although as we've seen we could tie this into that. So we're in R3, so here's the origin right there. It has to be the origin because that's where the two subspaces intersect. So suppose we have the subspace V is this plane, and we'd like to find all the vectors in R3 that are orthogonal to it. So that would be anything that pokes out here and anything that pokes out on the other side. So that's the idea. So once you kind of get an idea of how to think about this, you can visualize how this works. So in R2, for example, let's say we've got R2 here. If we had a line here, the orthogonal complement of that would be the line that is orthogonal to that. And all of those should go through the origin. The only reason they aren't in this diagram is because I can't draw well with my mouse. So we're starting to see something here. The dimension of V is 2, the dimension of this line is 1, and they add to 3. Here we're in R2, the dimension that we start with, well, I guess we started with this line, the dimension was 1, and so that only left one dimension for the orthogonal complement. So the orthogonal complement takes up all the remaining levels of dimension, is one way to say it. So let me clear this stuff off here and go to the next text box here. So the other thing, and this really is a key point of these orthogonal complements, is that any vector in the whole space, and I'm just illustrating this here with our example R3. So let's think about our example R3. Here's our origin. Let's suppose I pick a vector that sticks out like this. I can build that from one vector in each of the two subspaces that are complements to each other. So I can build a vector out to here, and then I can build this over to here, and if I add those two together, taking the tail of this one and putting it at the tip of this one, I would end up with something that looks like that. Again, those should really be parallel drawn, but I think you get the idea. And that decomposition is unique. I didn't write that here, but it's true. It's unique. There's only one way to pick a vector in the plane and pick a vector on the line that will add together to give some given vector. And this is not true just for this example with R3, where the V that we started with was a plane and its orthogonal complement was a line. No, it's true in general. So you give me some whole space, you give me a subspace V, and then we can take the orthogonal complement of V with respect to the whole space, and those two spaces now, the original V and then the resulting V perp, they work together to provide everything that you need. So you give me some other vector, you give me some arbitrary vector in the whole space, and I can write it as a sum of one vector in V and one vector in V perp. And that's a key idea, and we'll be using that in just a second. So what's so special about this from our perspective? We've been looking at, asking about two lines. They can be perpendicular in R3, but we know that those two lines could not be the row space and the null space for a 3x3 matrix, because they don't add up to 3 dimensions. They couldn't even be orthogonal complements of each other. So they can't certainly be the row space, can't be the null space. And what did we just say? Well, remember we talked about how the dimension of the column space and the dimension of the left null space, they have to add together to give the dimension of the whole space. That's exactly what we're seeing for orthogonal complements. So we need this condition to be row space and null space. We also need that same kind of interaction to be orthogonal complements. So we're actually starting to see here that because of the way that we defined orthogonal complements, the null space is the orthogonal complement of the row space, and vice versa. I didn't mention that, but once you have, so V perp is the orthogonal complement of V, but V is the orthogonal complement of V perp. They are one and the same. They go both ways, okay? And like I said, they kind of work together to build the whole space, in the sense that any vector in the whole space can be written as a linear combination of one vector in one vector in V and one vector in V perp. That's the cool thing. And since we now know, we've basically argued this, we have, and for the other two as well, the fundamental theorem of linear algebra part 2. Part 1 established basically this relationship up here, and the other one for the other two. That was part 1. It was about the dimensions and how they were related, but now we're seeing even more fundamental structure here. The null space of A is the orthogonal complement of the row space. So that tells us a couple things. It tells us that everything that's in the null space is orthogonal to the row space, but it tells us so much more. It's not just that. In a sense, this already tells us all the dimension stuff. It certainly tells us this relationship. It doesn't tell us that the rank, or that the dimension of the row space must be the rank of the matrix. That's the only thing that we don't get from part 2. So really part 2 captures almost more than part 1 does. And then we also know that the left null space is the orthogonal complement of the column space. So this is a big, big, big idea. And more important, this is really important, but something else that's just as important is that, remember we said that you give me a vector in the whole space, and I can write it as a sum of something in one plus something in its orthogonal complement. So you give me any vector in the whole space in which these two spaces lie, and I can write that vector uniquely with one vector in N of A and one vector in C of A transpose. And likewise, you give me a vector in the other space that's made up out of these two things, and you give me any vector in there, and I can write it as a linear combination, just a sum, really. One vector in the left null space, one vector in the column space. And that is powerful and remarkable. So let's take a look at this. So here's what we've got so far. We've been looking at this picture. We know about the dimensions. So the dimensions of the row space and the column space are both equal to the rank of the matrix. Big idea there. In fact, that's kind of how we define the rank of a matrix. Then we've got the null space. So the dimension for the null spaces are kind of what's left over. So if R is less than N, then there's dimension left over for a null space. And if R is less than M, then there's dimension over here left over for a null space. So, we could have both of these null spaces be more than just zero vectors. We could have one or the other be just the zero vector. Or we could have both of those null spaces be just zero vector. And so that's kind of the drives a lot of the distinction as to the different scenarios that we'll look at later. The other thing, I don't show it here, but remember we put orthogonal symbol here so that anything in the row space is orthogonal to the null space. Anything in the column space is orthogonal to the left null space. So that comes for free as soon as you know that they're orthogonal complements of each other. And here's the big idea. I really should have put this in a yellow box because this is a big idea. Every x, so remember we're talking about ax equals b. A is m by n, so x is n-dimensional. So the x's are lying over in this space. And remember, these two spaces work together to essentially build the whole Rn because they're orthogonal complements of each other. We've established that already. And that's why any x over here, so any x in this space, can be split into a row space component, so something that lives in the green box, even though it's not really a green box. So something that lives in the row space, and a null space component, xn, something that lives in the null space. And so let's see how that works. So there's an xr, and there's our xn. So there's going to be some point here, and we can imagine, like these are axes drawing. If we add those together, we'll get a point right there at where they combine. So there's our 2 points, and there's our x. So our x is this point right here. So you give me any x, it doesn't matter where it is. Obviously, if you give me an x that lies in the row space, then I only need the 0 from the null space. You give me something that lies in the null space, I only need the 0 from the row space. But you give me something that doesn't lie completely in either of those, and now I can build it from one thing in the row space plus one thing in the null space. And so there's that point. And so, we really should be thinking about there being a bigger space all around that. The green part only shows the things that are in the row space. The orange shows the things that are in the null space. And the other things have part in row and part in null. Okay? So that's where we're at so far. Let's talk about this a little bit farther. So what ends up happening? So this is kind of cool. We do AX. So A operates on this X. And where does it go? Well, we'll say that it goes into some B. And that B must be in the column space because that's the only thing that we can map an X to. So let's stop thinking for the moment that, like we normally do, that we know A, we know B, and we're trying to find X. Let's think of it the other way. We know A, we've picked an X, and we're trying to figure out where does it end up when I map it or operate on it with A. So I take A times X, and where does it go? It goes to some point here. But that's not the only one that goes there. It turns out that XR, its component in the row space, will also get mapped to B. And that's really, really easy to see if we imagine taking A and operating on XR plus XN, sorry for the scraggly writing here, is equal to, well, we pass the A through, A times XR plus A times XN. But XN, where does that live? Null space. So A times XN is 0. So this is just A times XR. We've done this little series of computations before. So A times XR gives us B, but so do other ones. Any X that is XR plus some other vector. So there will be lots of other ones. We can kind of stick with our drawing here and say anything that kind of maps back to this XR will map to the same B. So that's why when we have certain scenarios, when we have a matrix whose rank R is such that our null space is not just the 0 vector, there will be many solutions to AX equal to B. So you give me a B that's in the column space. It has to be in the column space because those are the only things that we can have a solution for. And we're asking, what gave rise to this B? Well, if we limit ourselves only to the row space, there's 1. But if we say we're looking for any X over the whole space, then there could be multiple ones, and that leads to multiple solutions. And so that's kind of the key idea that we're trying to point out here. And anything in the null space, anything here gets mapped to 0. That's its purpose. That's its null space. Everything maps to that point there. So we're starting to, we started with this simple picture, and now we're building, and now we should be able to see a huge amount of insight from this picture. Now, we've said that every vector, you pick any X over here, it has to go into the column space. That's by definition what the column space is. It's where things get mapped to. And so if we were to try to pick a B outside of that, then there would be no solution. There is no X that maps to something outside of the column space. So this is just showing that XR plus N, as we show here, and XR map to B, as well as, so XR plus any XN here will also map to B. So here's an exercise to finish this set of notes off. Well, actually, I think there's a little bit of concepts after this, but here's a 2x2 matrix. Let's take a look at it. We've got 1 and 3, 2 and 6. By now you should be able to start visualizing this and pick out, aha, I see, rank 1, right? This second column is just a multiple of the first column. So we know that the rank of this matrix is 1. Find the 4 subspaces. So here's our solution. If you want to pause the video, give it a shot, don't look at your notes, come back, and then I'll take you through it. So the column space, well, remember we said this column and this column are dependent, so we can just pick this as our basis. And so it's going to be any constant C times that vector. Now what about the column space of transpose? Well, again, we know that the rank of this is 1, so we know that the dimension of this space will be 1, and there should only be one vector then that spans it. And again, if we look at this row versus this row, we can see the second row is a multiple of the first one, so we can just take the first one as our basis vector, and so all the elements in the row space are just some integer, or not integer multiple, where did I get that? Some multiple times that 1, 2 vector. Now let's look at the null spaces. Well, again, from our dimension characteristics here, we know that our Rm is R2, Rn is R2, so our two big spaces are both two-dimensional, and we've got a one-dimensional column space, one-dimensional row space, so that leaves only one dimension for each of the null spaces. And you can easily verify that if you pick this vector and put it here, so if you put a 2 and a -1, that you'll get 0, so that is a basis vector. So any scalar times that vector is in the null space, and that creates the entire null space. And likewise, you can check that this is the left null space basis. And so if we draw these things, we can see a very clear, the simplest version of this bigger picture. So we've got this big picture over here, and now think about this picture while we're looking at this simplest version of it. So here we have the two spaces are two-dimensional. Now, none of this is just evocative. This is precise. So we've got our let's start over here. We've got our row space, which is characterized by the vector 1, 3. So here we go, 1, and then 1, 2, 3. Where do I need to be? Oh, column space is over here. So column space, yes. 1, and then 1, 2, 3. So there's a dot. We draw a line through the origin and that dot. So this line here is our column space. Let me clear off that ink. So there's our column space. And so we also know that the left null space is the orthogonal complement of that. So we can find it that way easily enough. Here's the line that makes the column space right there. We need the orthogonal complement of it. So that's one-dimensional. Our whole space is two-dimensional. So we need the one-dimensional space that's orthogonal to it, and so there it is. But we could also say, well, we've already found the basis vector for that, so it's going to be 3, -1. So we go 1, 2, 3, and down 1, draw the dot, draw the line, and we have that. So remember, we're showing these lines starting and stopping, but in reality, they go on forever in their respective directions. And notice how those end up working as if they are just two new axes for R2. So I can imagine that what I'm really thinking about is kind of rotating the axes this way. So you give me any point here and I can find its representation in this new set of axes. That's writing it in terms of one term in the column space plus one term in the left null space. So that's over here on the right side. That's our target space, where A maps things to. Let's go over on this side. There we've got our row space, basis vector of 1, 2. So we go 1 over 1, 2 up, draw a dot, draw the line. So this line here, that is our row space, and we're labeling that down here. And likewise, we know that that's one-dimensional. Our whole space is two-dimensional, so we need a one-dimensional orthogonal complement. That's going to be right here. It has to be orthogonal, has to be one-dimensional. But we could also come over here to this vector, measure over 2, down 1, draw the dot, draw the line, and that puts us in, or that makes that that null space. And again, it's like we've just rotated our axes, so we have two new axes. So you give me some x vector, and I can write it in terms of some element on in the row space, we'll call that x of r, plus some element in the null space, we'll call that x of n. So we can now write x is equal to xr plus xn. And then we're going to map. So what maps to where? Let me clear some of this stuff off. So xr itself will map to this point here. That would be the appropriate b. So if you gave me that as a b, I would say there is the solution to that. Or a solution to that. But what else could be a solution to that? Well, this point could be a solution to that, because anything that lies on this line is going to get mapped to 0. And so we would see the result would be this component getting mapped, this component getting mapped, and then the two components add together, but that component is always going to be 0. So in this example, you can see why we draw the evocative version that evokes this kind of setup, because this is the simplest scenario. And we can literally say, what are all the solutions that would arise if I said, there's my b. My b is 1, 3. Which b is that? Well, it can, what's the solution when b is equal to that? Well, it's this point. That's the one unique solution on this line, but it can be anything that lies on this line. If you go back to when we talked about multiple solutions, we talked about there being, the solutions were the null space, this is down here, offset by the particular solution. So xr is our particular solution. This null space line down here is all the null space vectors, and our solution space is this line up here. So that's how this works in this simplest case, and that's why we draw these pictures like this, and think about drawing these dashed lines. Well, I guess I don't need to get rid of that. We think about drawing these dashed lines as being evocative of getting some point in the row space plus some point in the null space. And we also think about, well, we could end up having anything along this quote-unquote line. In reality, it's not just a line. It's going to be some potentially higher dimensional space. It's going to be the whole null space moved up, perturbed, or offset by whatever the particular solution is. And so it's hard to visualize it in these higher dimensions, but in this case, it's very easy to visualize. And just want to credit, this picture and this example comes from the web page listed here. So let's back up. We've got these spaces. So let me clear all this ink off here. We've got these spaces. So we've got a row space, and we've talked about the basis for this row space. We've talked about the basis for this null space. Likewise, we've talked about a basis for the column space, and we've talked about a basis for the left null space. And we've talked about how these two blue ones kind of combine together through orthogonal complement mechanism to create the entire space Rm. So it would make sense that the basis for the whole space must consist of kind of a union of the basis for the column space union with the basis for the left null space. And likewise over here, we've got Rn is the whole space over here. Part of it is being spanned, the row space is being spanned by its basis. The null space is being spanned by its basis. And if we take the union of those two bases, we get a basis for the entire space. And that's what this last little bit is about here, combining bases from the subspaces. So as we talked about earlier, the idea of linear independence and spanning, we need both of those to be there to get to establish that we have a basis. We need spanning to ensure that we've got enough vectors to hit everything. And then linear independence says, but let's not get greedy. Let's not just put everything into our basis. Let's limit it to some smallest number of vectors that will do the job. So those two things together give us a basis. We'll hit everything from the basis, but we have a small set with which to do that. So in Rn, any n independent vectors must span Rn, so they are a basis. And likewise, any n vectors that span Rn must be independent, so they are a basis. And it's this view that allows us to see how the two bases for the two fundamental subspaces on one side work together. They get combined together. They're unioned together into a bigger set that is a basis, a legitimate basis, spanning and independent of the bigger space. And we can argue that, right? So to get a basis for Rn, we just need n independent vectors. Let's go back and think about this. So let's do this on the Rn side. We can do the same argument on the Rm side. So over here I need n vectors that will, n linearly independent vectors, and I've got a basis. So I've got R linearly independent vectors that are spanning the row space. I've got n minus R linearly independent vectors that span the null space. So those are my two bases, one for the row space, one for the null space. I've got R vectors up here. I've got n minus R up here. Totally, between them, I've got n vectors. This rule says if I've got any n independent vectors in Rn must span and must be a basis. Well, I've got n. I know, are they linearly independent from each other? Well, the ones in here are linearly independent from themselves. The ones down here are linearly independent. What about the whole group, all n of them? Yes, they are, because remember, these are orthogonal subspaces. So anything up here cannot be written from anything down here. So we get it, and we can do the same thing over here. And so we're just putting the final touches on the points and the kind of structure that builds all this. That yes, indeed, when we combine these two spaces together, we get a basis for everything. The same thing for the other side as well. So we've got R independent vectors spanning the row space. We've got n minus R independent vectors spanning the null space. And therefore, we've got a total n vectors. They are linearly independent. So together, they span all of Rn. And there's only n of them that span. So they are a basis. Now, let's look at the case to just close out here. I think this is the last one. Yes. We'll close out here with the case for an n by n square matrix. And so for that case, if the n columns of A are independent, that means that not only is this n by n and square, but it's n by n square and it's invertible. So it's an n by n full rank matrix. Aha! So the dimension of the row space is n. The dimension of the column space is n. So n minus n will be the dimension of this down here. And really this m here should be rewritten as n in this case. So our dimension of each of the two null spaces is 0. Just a little dot, just that 1, 0 vector in the corner of the row space, well, quote-unquote corner, and in the quote-unquote corner of the column space. There it is. And so we know that for an invertible square matrix, the solution exists and is unique. Why is that? Well, it exists because any vector that I pick over here will be in the column space. Any non-zero vector. Well, even zero vector, right? Because this is in the column space too. Any vector can be a legitimate B that I can map to. And where will the solution be? So you pick anything. This is in the entire space now. Column space spans the entire space. So there will be some vector over here, X, that will map over to that. Are there any others? No, there are no others because the null space is 0. So not only does a solution always exist regardless of which B I pick, but the solution is unique. It's beautiful. This is how we see this nice case, and then the other pictures are how we see the not so nice cases. So hopefully these ideas are starting to solidify in your brain. Think through them. Understanding them is key. Like I said, this course is not about how do I get a frickin' number. It's not about getting the frickin' number. It's about figuring out how to think about this stuff. So think about it. And I'll see you in the next, I almost said in the next vector space. I'll see you in the next video.